Hello, I'm John. I'm the CTO of Veridise. We are a blockchain security company, but one thing that we specialize in is zk circuits. We've been working with Aleo a lot lately, and so I'm going to be talking a little bit about common vulnerability patterns in Aleo. We're also going to have Kostas, who's sitting over there right now, who's our chief research officer, who's going to take over at some point. Okay, so first let's talk a little bit about the execution model, because as I'm sure many of you are aware, Aleo integrates zk with traditional blockchain smart contracts. However, there's kind of an awkward synergy between these two types of technologies. So in particular, zero-knowledge circuits are stateless. They have restricted control flow, which means you can't do like arbitrary looping behavior and conditionals. In addition, they use finite fields as their numeric type versus integers and stuff like that. And they also allow for data privacy. So you can have private data and public data and operate on them without exposing private data to the external world, hopefully. Smart contracts, on the other hand, are persistent, meaning that they have storage that is going to persist between invocations of the contract. They allow traditionally arbitrary control flow.
Usually, their numeric data type is affixed with integer rather than a finite field, and so the difference is a fixed width integer is going to be 2 to the power of something, whereas a finite field is going to allow numbers up to some large prime to be expressed. And finally, smart contracts always make the information published on the smart contract public. So if you want privacy, you have to integrate with some other technology like zero-knowledge circuits. So let's talk about how one makes these two technologies interact. And this is the model that Aleo takes. And so essentially you've got a person. A person is going to invoke the circuit side of the Aleo contract, and then they're going to get a proof. Then they're going to take that proof and they're going to check it into the Aleo blockchain where it's verified and added to the blockchain. There are a couple of different languages that we've seen here that use the exact same model as Aleo, and so I've got kind of a snapshot of some of the other ones that we have worked with quite a bit. And we can kind of look at some of the design decisions that have been made, because not all of them integrate with zk in exactly the same way. So the 3 languages that I have here are Leo, O1JS, and then essentially making your own private integration by using a combination of Solidity and zkCom. And so the important thing here is we can see some of the design decisions that have been made by individual teams, and we're going to see how this affects the, in this case, Aleo system. But essentially for Leo, the important thing is the base storage type that they use is a finite field. Because they are building on top of zk circuits and they want you to express everything in a single contract, their control flow is restricted, meaning that Aleo still doesn't have arbitrary looping behaviors and stuff like that, even in their smart contract. The logic between the smart contract and the zk circuit is separated, which means that you're not writing a single product and then compiling it down, and that will execute on the zk circuit and the smart contract. In Aleo, you have this differentiation between the circuit logic, which goes into the transition function, and the smart contract logic, which goes into a finalize function. And we'll look at that in a little bit. And then finally, some of the languages allow people to create explicit zk proofs. And so this would be by executing the zk circuit themselves and then verify that proof on chain. Aleo, however, makes this process implicit. When you execute a transaction, it's implicitly going to construct the proof for you and check it in when you check the proof in with the blockchain. So I'm mostly focused on Aleo here because that's going to be the topic of this talk. I do think that it's useful to kind of see the other decisions that other teams have made, but now we're going to not look at those and focus specifically on Leo. So for those of you who maybe aren't familiar with Leo, we can essentially divide the logic of a transition into two different steps. So you have the transition logic, which is going to be your zk logic, and then you have your on-chain logic, which is going to execute when the proof is checked in on-chain. And there are restrictions about what you can do in both. So for example, in the zk logic, you can't access state variables and stuff like that. You can only do that in the on-chain logic. So you can only access state variables in a finalize function. In addition to that, one thing to be aware of is in the zk logic, your arguments are going to default to private variables. And so you can see here in the first argument, I specified that as public, but in the remaining arguments, I didn't specify a visibility, and Aleo is going to default to private. However, if we look at the finalize function, I did the exact same thing, but one interesting thing about the finalize function here is that because this is on-chain, and like I said, everything is going to be public on-chain, you actually can't have private arguments here, and when I don't specify visibility, they're going to be public. So this is one thing to be aware of, is in the on-chain logic, everything will be visible. In the off-chain logic, you can have privacy, and then you split up your logic between zk and smart contract in this way. So let's take a look at some common vulnerabilities that typically pop up in Aleo as well as other zk languages. So the first one that I'm going to talk about is missing state validation. And so what I mean by that is because a zk circuit doesn't have any way of determining the current on-chain state, it has to be provided by the user. And so in this case, you might have a user claim that the current state is X, but on-chain really the current state is, or the current state of X is 0, but on-chain the current state of X is actually 5. And so because the zk circuit can't check for the validity of that state, you instead have to perform the check on the smart contract side. And if you don't perform that check, then essentially any operation that you perform in the zk circuit, assuming that the state is correct, might be wrong. So as an example, we can take a look at this like private transfer function. So in this case, someone wants to keep balances private or something like that. So what they do is they allow the user to pass those in, and then they'll perform or adjust the balances in the transition function, and then they'll just tell the finalize function to adjust the balances. However, the important thing here is that because they aren't actually validating the balances of the balances that were passed into the transition function, someone can actually lie about their the balance that they have on chain, and therefore essentially gain arbitrary funds. And so one thing that's very important to do in systems like this is ensure that any state that you're trying to access in the transition function has appropriate validation in your finalize function. The next thing that I want to talk about is an arithmetic denial of service. And so what I mean by this is zk circuits have restricted control flow. And so that becomes particularly important because it makes it a lot harder to avoid errors like integer overflows and stuff like that. Because while Aleo allows users to specify computations over fields, they also model smaller bit width integers like U32 and stuff like that. And in these smaller bit width integers, they specifically disallow integer overflows and stuff like that unless you use a specialty operator. And so if that is not the desired behavior for your application, you might want to like add in a conditional to say, if this could possibly overflow, do something else. However, in Aleo, you'll always execute both sides of the conditional, which means that if you're trying to avoid an overflow by just saying, if it's ever possible to overflow, then, like saturate or do something like that, then you're actually not going to avoid the error because the add that performs an overflow or something like that is still going to be executed. So if we look at this particular example, essentially a user is trying to perform a saturated add. And so what they do is they check to see if the resulting balance is possibly larger than the maximum int that could be expressed in a U128. And then based off of that, they'll either saturate to the maximum U128 or they'll go ahead and perform that add. However, the problem here is, like I said, because both sides of this ternary operator are going to be executed. In addition, even though ultimately what's going to happen is you should set this to max U128, you're actually going to end up always overflowing in this case because it will always still execute that val plus amount. And so in this case, even though it looks like you'll avoid this error condition based off of the control flow, it's not actually going to happen. Okay, so the next thing that I wanted to talk about was signature replay attacks. So signatures are commonly used in order to prove that someone has, approved a particular action. So they will sign a hash in order to say, yes, this is something that I actually want to do. However, it's possible that if the signature is not set up carefully, an attacker can go and reuse a publicly available signature in order to replay that particular action. So let's take a look at how this might happen. So we can say that this is an approve function. In the approve function, it's going to take in a signature, and then it's also going to take in the person to be approved, as well as the particular amount that we want to approve that individual for. And so in the finalize function, the finalize function is going to take in that signature, and it's going to verify that the signature is correct. And if it is, then it's going to set that approval. However, the problem here is that because there isn't a nonce or anything like that, it's always possible to replay that signature with the same arguments. And so what I mean by that is there is nothing checking to make sure that signature can't be sent to the finalize function again. And so without any way of specifically disallowing this signature in the future, the person who is being approved in this case could just take the signature, which is going to be publicly available on chain, and replay it again in order to get approval over and over again in this particular contract. And so really what the user is missing here is some sort of checking mechanism in order to check for repeat signatures, which is typically performed using some sort of a nonce, so that a user can only use a nonce once. That way, if someone tries to use this signature again, it will determine that the nonce has been used, and therefore the signature is invalid. Okay. So the next issue that we wanted to talk about was finite field overflows. So we talked briefly about how Aleo allows both computation over finite fields to be expressed, as well as computations over smaller bit width integers. The interesting thing, though, is that for smaller bit width integers, Aleo has automatic overflow checking and will revert if that integer could possibly overflow or does overflow. Well, they don't have the same thing with finite fields. With a finite field, they're perfectly happy to allow an overflow. And so in that case, if that's not desired behavior, you have to add that in yourself. And so, for example, if someone were to use like a field for these transfer functions, someone could cause an arbitrary overflow or underflow in order to gain a large balance. And so in this case, you have to be cognizant of what data types you're using and look for those underflowing or overflowing or underflowing behaviors, because it can be really, in some cases it might be desirable to allow them, but in many cases it's not. And so here, if you're using a field, you would need to add in additional checks in order to make sure like someone can't underflow from 0 to a really large finite field, or overflow from a large finite field to 0. Okay, the next thing that we want to talk about is privacy leakages. And so privacy leakages are very important because Aleo is a private blockchain. And so a lot of users are developing private applications where they don't want to expose private user information. And so we're going to talk quite a bit about privacy leakages because it becomes very important to ensure that information is not leaked. People can't learn about this private information. And we've seen a lot of errors here where people accidentally leak information in a couple of different ways. And so I'm going to have Kostas take over and talk about some of the ways that we've seen people leaking information in their zk circuits or their contracts.
All right, thank you, John. So yeah, as John mentioned, we're gonna talk about privacy leakage, and I guess like since we are like in Aleo workshop, right? Like a natural question to ask is like, doesn't like zk mean like zero knowledge? So where do the privacy leakage come, right? If you were here yesterday, a lot of people will talk about like how things are private, and they were taking that for granted, right? So zk means there is zero knowledge, but there is like, the usual cuts, right? Like, you have to implement things correctly. So we're gonna talk a little bit about like, several cases we have seen in past audits, not all Aleo specific audits, like, that applies in any kind of like, privacy preserving application. But on a high level, when do privacy leakages happen, right? So as John mentioned earlier, our circuits are gonna handle both public and private information. And then eventually, like, the public information will be posted on chain. So a leak is gonna happen when like the value of a secret can influence the value of a public information that eventually is being posted on the blockchain. And by all means, this is not like a zk specific problem. Privacy leakages have been happening since the Web 2 days. However, in contrast of the Web 2 days, where the public information was sitting behind like some companies' servers, now like the public information is like actually public. So let's now go and see a very like simple and like almost like silly example on of how like some private information might be leaked. So here we have like a simple transaction that like given a private field and an owner, it does some sort of do we see the clicker? Okay. It does like a multiplication between like the private and like some constant, and then like it calls finalize, and then like this value goes and flows into the blockchain. So here, as you can see, if like an attacker knows the source code of this contract and sees a finalize with a public value, then they can essentially reveal the secret because this multiplication here is invertible, right? I just do a division and like I now know the private value of this transaction. So let's go and see a bit more of a more complicated example where like the leak is not like as apparent. So here we have like a transaction that tries to mint some stuff for a user, and we want this minting to be private. So instead of posting the actual value that was minted into the blockchain, we first hash how much like the user had before this mint, then we hash how much they will have after the mint, and we pass these hashes into the blockchain. However, this contract, instead of like only tracking the balances of a specific user, it also tracks the overall balance that has been minted already. So this logic happened here, right? We have a total that is being updated by the amount that we just minted. As you can see, like now I don't expose the balance explicitly, but by observing this addition here, I can like tell how much was the increment, right? Because like I know the previous total and the new total, so by taking the difference, now I know how much this operation minted. So if I see the history of all mints for a specific user, I can like I can infer their total balance. And yeah, the culprit is like that store over there that like essentially it will let us know like the diff of every mint. Let's now go to an even more complicated example, and this is kind of like a thing that we have seen in like several audits. Not with this like type of application, like I just made up a silly application here just to demonstrate how secrets can leak in a more of an implicit way. So here we have like imagine like we have an auction where bids are blind, so I don't reveal how much I bid for an item. And also let's assume that like I have like a maximum amount of bids of value that like I'm allowed to bid, like so the auction has a cap. So this auction also has like this special feature where a user can prove that like their current bid is like at least some like minimum amount, and then they can use this amount to like as a collateral to request like loans so they can bid more and things like that. So this transaction here does this exactly thing, right? We don't reveal our current bid, we just like hash the current bid. Then we assert that our current bid is like, larger than like a floor. And then we call finalize with the hash of the bid floor. And then the finalize will assert that like, whatever we post like as a hash function equals to our current bid. It's like, the issue that like John said earlier that we have to check that like, the user is being honest. And then it's gonna say that like, our current floor is like this thing. So now let's assume that like our auction also has the ability to, reveal the current winner, right? Like, you call this function and then you find who's currently winning the auction. So now let's assume that our winner, for some reason, wants to use this collateral function and calls this and invokes like this transaction. So now for the rest of us, we're not like winning the auction, since there is like a maximum value for this auction. We now have like a minimum amount for like, the current winning bid. So if we want to outbid the winner, we kind of like limit the values that we have to kind of like, search for. So it makes kind of like easier for us to, outbid the current winner. So as we see, like designing and implementing a privacy-preserving application can be indeed very tricky. And generally, when do secret leaks happen? As we saw, like if there is a flow from a private input to that of a public input, then attackers will essentially have the opportunity to learn some sort of like information about like our private data. And as we saw, the flow can be either explicit or implicit, right? Like as we saw in the previous example, we don't like have like an explicit flow from the private to the public. We just have like a comparison, essentially that like reveals this type of information. So we have to be careful to make sure that the flow is like neither explicit nor implicit. So let's move on to see how we can prevent such privacy leakages from happening. So first thing first, like we need to like essentially know our crypto, right? Like for the first silly example, where like the operation is invertible, we need to make sure that like, we're using a cryptographically secure like trapdoor where like, the attacker cannot like invert the computation. Otherwise, we have to be like really careful and see if like we have like any of these dependencies I mentioned earlier. And also since we're Veridise and we are developing automated tooling, this can also be automated. And if you're interested, we can discuss things offline. So. But like in the case where, we determine that like this is the case, right? We have like in our current protocol, we have some public information that their value depends on a secret. What should we do? So first of all, probably we have to redesign our protocol, right? Instead of like posting this public information to the blockchain, we have to modify what we're posting. And then again here, crypto is going to be our friend, right? Instead of like posting the public information directly, we're going to have like a hash function and then introduce the appropriate checks on the smart contract to avoid leaking any information. So speaking of that, like when we do redesign our protocol to be secure and like introduce all these extra layer of protections, we again have to be careful. And we just, because like, one solution one can do is like just has everything, right? But even then, we again have to be careful. So in the 2 of the 3 examples I showed you, there was like another privacy leakage. And I'm wondering if any of you kind of like noticed the issue. So just to give you a little bit of help, it's like these 2 examples. Okay, so I can even like narrow down like the scope. So it's gonna be here. Any ideas? So here the intention is like, when we try to hide our bits, right, we just say has the value of my current bit and then post that to the blockchain so an attacker cannot invent that, right? But a bit is going to have like an expected range, right? So I cannot invert that, but I can calculate all hashes from 0 to like, whatever value. And, whenever I see a hash, then I can like, invert this computation because like I now have like a dictionary. So, and the same thing holds for the other example. So how do we avoid that? So we need to use some randomness, like surprise, surprise. So instead of like just putting the hash, we introduce a salt, which is going to be like a large random number. And then every time the user wants to use the protocol, they need to remember the salt they used and reuse it to like, calculate the hash. So this way, we kind of like increase the search space an attacker will have to explore in order to perform a dictionary attack. So I think that concludes all the things we have to say about, privacy leakage. And overall, we saw today that designing a privacy-preserving protocol or like, a zk protocol in general, whether like, it has some privacy features or not, it can be really tricky. And as we saw, bugs can happen either on the circuit or on the blockchain or anywhere in between, right? Because you might have implemented each of the components correctly, but the interaction of the two might actually introduce some very tricky bugs. And I think that's all we have for today. Thank you so much, and if you have any questions, please let us know.